Hey everyone, and welcome. Today we're tackling Leetcode problem 1233, remove subfolders from the file system. The name gives us a pretty good clue what it's about. We're going to dive into what that means, look at a few really cool ways to solve it, and see how different data structures can make a huge difference. Let's get started. Alright, here's the official problem description. Essentially, we're given a list of strings, where each string represents a folder path. Our job is to go through this list and clean it up by removing any folder that is a subfolder of another folder also in the list. We then return the cleaned up list. So to put it simply, we're looking for the most general or highest level folders. If a folder like /a is present in our input list, then any other folder that lives inside of it, like /a/b or /a/b spaties, is considered a subfolder and needs to be removed from our final result. Now this part is super important. The definition of a subfolder is very specific. It's not just about one string starting with another. For a folder B to be a subfolder of A, it must start with the entire path of A, immediately followed by a /. So, /a4b is a subfolder of /a. But /ab's not, because it's missing that crucial /separator. This little detail will guide all of our solutions. Let's walk through this example to make it concrete. We have a list with 5 paths. We look at /a/b and ask, is its parent, /a, also in the list? Yes, it is. So, we flash a/b for removal. Then we check /a/a/a/a. Is its parent, /a/a/a/a in the list? Yes again. So /a/a/a is also out. The remaining 3 paths don't have a parent in the list, so they are our final answer. Okay, let's think about our first approach. A straightforward idea would be to take each folder and, well, check if its parent exists in the list. To make that check really fast, we can first dump all the folder paths into a hash set. This gives us nearly instant lookups. So for any given folder, say /a/b/c's, how do we find its potential parents? We can just slice the string at each /. This would give us /a and /a/b's. We'd then look up both of these in our set to see if either one exists. Here's a possible implementation of that idea. It works, but it's not the one from the editorial, which is a bit cleaner. Let's look at the official, slightly more elegant version. Okay, this is the official code for the set approach. It's a little more direct. It adds all folders to a set for quick lookups. Then, for each folder, it works its way upwards, checking for parents. Let's break down how that while loop works. First things first, we convert our input list into a set. This is a classic optimization. Checking for an item in a list can be slow, but checking for it in a set is, on average, instantaneous. Then we just prepare an empty list to hold our results. This is the clever part. For each folder we start a loop. Inside the loop, we repeatedly chop off the last part of the path to get its parent. For example, if we start with /a/b/c, the first chop gives us /a/b. We immediately check if /a/b is in our set. If it is, we've found a parent. We can set a flag and break out of this inner loop. If not, we continue, and the next chop gives us /a. We check that, and so on, until we run out of path. Now for a much more elegant solution. What happens if we sort the entire list of folders alphabetically? A really cool property emerges. A parent folder, like /a, will always come immediately before any of its children, like /a/b. This structure means we no longer have to search all over the place for parents. This observation simplifies our algorithm dramatically. We sort the list. The first item is automatically a root folder, so we add it to our results. Then, we just walk through the rest of the sorted list. For each folder, we only need to compare it to the most recent folder we added to our result list. If the current folder starts with that last result path plus a /, we skip it. Otherwise, it's a new root folder, and we add it to our results. And look how clean the code becomes. We sort the list in place. We prime our answer list with the first element. Then, we loop from the second element onward. The check is simple. Does the current folder's path start with the last answer's path plus a /? If not, it's a new root, and we append it. Beautifully simple. Alright, let's talk about the most advanced, but also the most conceptually fitting, solution. A trie, also known as a prefix tree. Whenever you see problems involving string prefixes, a trie should pop into your head. We can model the entire file system as a tree, where each node represents a directory. So when we insert a path like /a we press C, we traverse from the root to a node for A, then to a node for B press C. At that B node, we'll place a special marker to say a complete folder path ends here. We do this for every path in our input list. Now how do we get our final list? We simply walk through the trie, starting from the root. The moment we hit a node that we've marked as an endpoint, we add its full path to our result, and then we stop going down that branch. By not visiting the children of an endpoint, we automatically ignore all of its subfolders. It's a perfect fit for this problem. The code is a bit longer, because we have to define the trie structure itself, but the logic is very clean. We have a trie node class, a main function to build the trie, and a search function to collect the results. Let's quickly look at the pieces. First, our trie node. It's a simple class. It has children, which is a dictionary that will hold all the subdirectories. And it has a ref field. We'll use this to store the full folder path string, but only if a path actually ends at this node. Otherwise, it will just be an empty string. Next is the build process. We loop through each path from our input. We split the path into its components. For each component, we travel from one node to the next in our trie, creating new nodes along the way if we need to. When we reach the end of the path, we set the ref of that final node to be the complete path string. Finally, the search. We use a simple depth-first search. The function checks the current node. If its ref field has a path in it, we've found a root folder. We add it to our answers, and, crucially, we return. We don't explore any deeper. If the ref is empty, it means this is just an intermediate directory, so we continue the DFS on all of its children. So let's compare these three methods. The set approach is the slowest, with a complexity related to the square of the path length. Sorting is much better, bringing it down to n log n, which is a very standard sorting complexity, but the trie wins on time complexity. It gives us a linear time solution, which is typically the best we can hope for. Both the set and trie approaches use extra space proportional to the total size of the input data. So what did we learn today? First, there are often many ways to solve a single problem, from brute force to highly optimized. Second, never underestimate the power of a simple sort. It can often reveal a hidden structure in the data that makes the problem much easier. And finally, for any problem involving prefixes or paths, the trie is a data structure you should always have in your toolkit. I hope that breakdown was helpful. If you found this useful, please hit that like button, subscribe for more Leetcode explanations, and feel free to leave any questions or alternative solutions in the comments below. And hey, if you're feeling extra generous, the Boba Fund is always open. Thanks for watching, keep up the great work, and I'll see you in the next one.